Okay, so today's video is going to be a longer one. So this video is designed to teach you the secrets to make your dirt bike run on methanol. I haven't seen a very good full-length presentation that goes into detail as much as I go into. My apologies for the length. At the start of the video, I'm going to cover the basics of what you need to accomplish to maximize your power output from methanol, and I'm going to go in depth from there. It's going to get really in depth. So I'm going to cover the basics. So what you're going to need is you're going to need one of these little itty bitty hand drills. You're going to need a special drill set that has drill bits in step size of 0.1 millimeter. They're not too expensive. This was like 70 bucks, 60 bucks, something like that. For some Keihin PWKs, you need to get a security bit driver set to get into the little security frustrating Torx type bits that have that stupid little bump in the middle that prevents you from using a Torx driver. You're going to need the ability to make a custom needle, which is not that hard. I personally used my neighbor with a lathe because I work traded and was able to get some help from him. However, it would be trivial to either make a guide out of wood or 3D print a guide with the correct needle angle that you need to calculate, which we'll get into, right? Idea being you take your needle, chuck it up in a drill motor or a drill press, and hand sand it down and then check against your gauge. That's not hard to do. Anyone could do that. So I'm going to put it up front. You need to do a tiny bit of drilling with the itty bitty driller tool, and this is all turned by hand, not in a power tool for the itty bitty drill bits. You need to be able to drill out passageways in your jet block. They call this guy the needle jet, and you can do that with a hand drill. You also need to be able to drill out your float, and you need to make sure that your gas tank can flow the right amount of fuel. So if you think you can do those things, this video is for you. And we're going to teach you the science behind how to accomplish all this. Now, important to note, if you're going to do this, please think it through and understand all steps of the process. Now, I also highly recommend a high compression head and have a local speed shop help you with that. My bike's a kx100. It's a super mini for adults, not for kids, and it's a ton of fun. The kx100 shares the cylinder of a kx80 and kx85, just bore size is different. So that means the case halves and crank and all that is the same, and the cylinder heads would bolt on if you account for everything appropriately. So I had a kx80 cylinder head sitting around, and that has a much smaller chamber volume, right, in that cross-sectional. Basically, you can get a kx85 or a kx80 head, and you can start from there with a default smaller chamber, and you don't have to fly cut the cylinder head as much. So this is the original kx100 head. So, right, the shop needs to set the bore, set the squish, and set the chamber height for high compression. It'll run without high compression, but you won't see as much benefit. You also need to be able to adjust your ignition advance, and so some bikes have the stock stator plate that can be adjusted to account for that. I personally use a programmable ignition unit. So those are the prereqs. If you can handle that, you can handle figuring out methanol. It's not that hard. So what do you get if you do methanol high compression and ignition advance? I saw about a 15% bump over gasoline in terms of total power output. That 15% is no joke for not a whole lot of work, not a whole lot of investment, and if you take your time and understand the science and do the math yourself, your investment in time and energy in modifying your carb is very minimal. I went through about half a 5-gallon can tuning the methanol system, and it was done. And that included some of the dyno pulls, including riding to the dyno pull area and back. We'll talk about the dyno stuff at the end of the video. So if you can handle a little bit of drilling work by hand, you don't necessarily need a drill press. Doesn't hurt ever to have drill press. Drill by hand. Also drill by hand. And if you can handle getting a little security bit driver set and drill bit set, then this is for you. Cutting the custom needle can be done with hand tools and sandpaper and stuff like that. This is a Keihin FCR 39 4-stroke needle. It's off like most all the 2000s dirt bikes. It has a bigger diameter, so you get more to work with when you cut it down. Here's a stock needle. So this video should apply to pretty much all Keihin PWKs. I know there's some bigger ones like on the Banshee quads and stuff like that, but I've never seen a really good in-depth explanation for the small two-strokers. So let's get into it. Good evening, everyone. Today I want to teach you how I set up a Keihin PWK 28 carburetor for running on methanol on a two-stroke. Now, it's really not that hard as long as you understand the core concepts and you think through the science on how to solve the limitations of a stock carburetor. So, straight off the bat, gasoline has a stoichiometric air-to-fuel ratio of 14.7 to 1. Methanol has a stoichiometric ratio of 6.4 to 1. What that means is you need 1 part of fuel for every 6.4 parts air, and then the same idea for gasoline. That means you need about 2.3 times the amount of gas or methanol passing through this carburetor into the engine. Now, that 2.3 is minimum. I would not allow any less fuel than that. You don't want to run lean on methanol. You don't want to have methanol detonation in your engine. So that 2.3, that's your minimum right there. Now, so the core concepts of the modifications here, those are going to apply to any race gas that's oxygenated that requires more flow to be at its correct mixture ratio. In order to maximize your benefit from methanol, it's not just flowing enough fuel. Ideally, you increase your compression ratio inside your engine so that it squeezes that methanol really, really tight and you get much better explosions. In addition to increasing the compression, you're also going to need to play with your timing a bit. Now, I won't say what you need to do in your specific case. I will tell you what I have done in my specific case, and you could apply that to yours. However, my case is a little different than most people's. I have a programmable ignition unit, a programmable CDI. The stock CDI is in a box somewhere. But basically, I can plug my laptop in, which you should have seen in the intro video, and I can tune the ignition curve at any RPM. So on the big end of the RPM spectrum, I'll throw up the image of my ignition curve, but I'm not going to include the actual advanced numbers on it. Very good reason for that in a minute, but let's throw that curve up. So in red is the gasoline ignition curve that I was running on that I tuned for, and in blue is the methanol ignition curve. Now, from my testing, I found that it did not like having more advance in the mid-range. As you can see, I didn't advance it much further beyond the red curve. But on the big end, it liked having more advance. And I actually did the data pulling to verify that I was getting slight benefit from adding more advance. It's possible that I could continue adding advance on the big end, but I haven't taken the time to go and test it. I only saw some fairly marginal but present gains in the power output when playing with the advance. So the advance makes a difference, and it's just a matter of taking the time to verify what you're doing, because the percent changes you'll be seeing. I'll throw up the chart here, and again, I'm just going to show you the shape of the curve, but I'm not going to show you the actual numbers on the left of the column. So let's throw that curve up. You get to see on my right, I've got a bunch of I got a naming scheme describing which curve was used. So I did usually 3 or 4 pulls on each curve. And two strokes are funky. You don't get this exact same pull every single time. But that being said, my dyno is a little unconventional. We'll talk about the dyno a little later, and we'll talk about the dyno charts it produces a little later. Before we get to that, I just want to point out the basics. You need more flow area. You need a high compression head. I've got the low compression head in there, but won't forget about it. You need a higher compression head. Rephrase that. You benefit from a high compression head, and you benefit from adjusting your ignition curve. You could run methanol with just the carb. You may or may not get that much benefit. It really depends on how much time and effort you want to dedicate to tuning the ignition curve, and it depends on your hardware limitations. Now, on a stock bike, what you can do is you can adjust the position of the stator plate within the generator housing, and what that will do is that will advance or retard the entire ignition curve. So when we throw up that picture of that ignition curve, that would raise every point along that curve, right? It's not just going to advance just one end, it's going to advance the whole thing or retard the whole thing. So you don't get the granularity, and you may run into a little bit of knock detonation in one area, whereas like on what I found, I was able to add more curve on the big end on the side. So a high compression head is not that big of an investment. Working on the carb, also not that big of an investment. Depending on your ignition unit, also not that big of an investment. I'm running an Ignitec AC CDI-P. That's the part number, model number rather. And that is the programmable CDI unit that runs on an AC system. So most dirt bikes run off AC coming off the generator. There's a handful of bikes like the dual sport bikes or bikes with a headlight that will run a little rectifier setup like this with a capacitor, and it'll make a 12 volt DC signal or power for the lights and battery and starter and all that kind of stuff. And so some of those CDIs are 12 volt CDIs. So high compression heads, not too expensive. Programmable ignitions, not too expensive. I have been able to show about a 15% power increase by adding compression, methanol, and ignition advance and tuning everything for that. It's possible I could get a little bit more power by decreasing the jets a little bit. I'd rather be on the rich side and be careful than be on the lean side and burn a hole through the piston. So we're going to dive in to the carburetor here. So we're going to switch over to this view. I'm going to show you. Oh, no, before we dive into the carb, we need to talk about flow restrictions. So flow restrictions, you may think they exist in here. You're right. But they also exist in here. This petcock has a filter on the inside and an inline filter right there. I did a ton of testing on that setup. And when I went to a race that had long straights in a canyon wash, the fuel tank was actually too slow to keep the bowl full. That fuel tank is not equipped to flow minimum of 2.3 times the amount of methanol to keep the bowl full. We need to measure its current flow rate, so it's pretty easy. You just fill it up, set it on something, put a measuring cup beneath it, open up the petcock, time it, see how long it takes to fill up a quarter of a liter, something like that, and then you make your changes to the flow system, measure it again. So that will eliminate that problem. However, there are more restrictions in here that we need to talk about that you need to modify. And once you modify that to flow more, verify that you get the same flow through here. So let's talk about where your flow restrictions come. So we're going to switch over to the little camera here. So your float valve, your shutoff that shuts off the flow into the bowl, right? That guy chills in here. And when the rubber conical surface, come on, focus. When that rubber conical surface contacts that cone-shaped hole up in there, right, it seals. So you make the hole in here bigger, but you do not exceed the maximum size of your piece of rubber. If you do, it will not seal, and then it will always be flowing fuel. And it'll go through the overflows, and it'll flood you out. So you don't want to do that. So I made this, I think it was either a 2.9 or a 3.0 millimeter hole. I think it was, yeah, 3.0 or a 3.1. I don't think you want to go much further beyond that. So I'm not going to do the testing tonight on the gas tank, but when we do, you also need to make sure that the flow area around I'm going to grab something small that I can poke with. That gap around there, you need to make sure that flows enough to meet the same flow rate that you accomplish by modifying your gas tank. And if you look closely in here, let's see, there we go. See that? See, there's a tiny little hole right there. And a tiny little hole on the other side, right? So there's multiple orifices that fuel can come out, right? It can come out that side, it can come out the bottom, or that side. So if this doesn't flow enough, we don't want to enlarge the bore here. We don't want this thing to be crooked like that. So we can add more holes here or enlarge those holes. Okay. Now, oh hey, important note before I forget, this is a little jet block, if I'm not mistaken, that's what they call it. That guy sits in here. It's got a special gasket. You usually don't get this gasket with the carb rebuild kits, and we do need to get down into this area. Okay, so we're talking restrictions. So gas tank, float. Now, obviously, the jets need to be changed, right? There's your main jet, there's your pilot jet. Jets need to be changed. Not as common, but still needs to potentially be accounted for, is this hole right here. So you saw the position this guy sits in. The pilot jet feeds through there, and it comes out that hole. Let's turn that flashlight on right there. So it's getting sucked out as the vacuum pulls it. So I don't have anything small enough to measure what that stock hole size was. This is a stock Keihin pilot jet. It's like the biggest one they make, and it just so happened that the jet size calculations told me to use that one. It's very possible that stock jet and stock orifice would have flowed appropriately. However, I didn't want to risk it. So I drilled this hole out to a 1.1. Now, something else I highly recommend that you acquire. They call these like a little engineering drill bit set. But if you looked closely, the 1mm drill bit was already gone. That's because yours truly forgot the rule that I made for myself of don't put tiny drill bits in power equipment. So you need to get one of these little guys. My neighbor gave me this. And I personally reached through the front side rather than trying to come in at an angle here because the angle was just wrong. You'd basically need to be here. But you can get at it from here. And you just very gently and carefully hand turn it with just a tad bit of pressure. It takes a while, but it'll go. I made this hole a 1.1. It's possible that there may be some slight aeration that kind of happens as it gets sucked through the tiny hole. I don't know for sure. It's hard to say. I haven't noticed any off-idle problems or any tuning that needed to be done in here. So, like I said, this was the biggest Keihin pilot jet, if I'm not mistaken. So, like I said, it's very possible that PWK has a orifice size that could handle it, but it's better to be safe than sorry. It's better to be on the larger side. It probably would be ideal to go get a maybe an inch drill set that goes below that size and just kind of gently work your way up till you find that 0.62 millimeter hole size. I just didn't want to risk it. There's a restriction. Okay, obviously the main jet needs to get swapped out, right? So, very important to note, on the other side of this, they call this the needle jet. That's what they call it on the exploded parts diagram. The needle jet purpose is to handle let me grab the slide here. The needle is an incredibly important piece to this puzzle. What the needle does is it changes the size of the opening that the main jet is allowed to flow fuel through. You can make this thing as big as you want, but if this is smaller, it doesn't matter. So I think the stock one on this PWK 28 was a 2.6 millimeter. This is going to segue into a difficult to explain topic without my Excel sheet to show you the calculations. So I'm going to show you that later. Let me explain the basics. I'll use this guy And we'll get nice and close up here to show you. Okay, right there, this is just an illustration, right? But this is what you could imagine for a throttle closed position. The fuel that is allowed to flow past this guy is a donut-shaped area. As you bring this tapered needle up through that hole, that donut shape, the area that fuel can flow through that donut shape gets bigger and bigger and bigger, right? It is a nonlinear relationship. Nonlinear relationships are not easy to solve just by winging it or just by testing and just throwing parts at it, basically. So I did my best to figure out if a stock needle with a drilled out jet could provide adequate fuel throughout the entire range. Remember, we want about 2.3 times the amount of fuel everywhere. Not just idle, not just full throttle, across the entire range. Long story short, through my math work, which I will show you later with the Excel sheet, I determined that I needed to enlarge that hole and cut a custom needle with a custom taper. So the stock taper is a 3 degree, and this guy, I'm going to line them up here. This custom cut one is a 6 degree. So when you pair the bigger hole with a bigger, stronger, faster taper, I was able to maintain very close to these equivalent flow rates. Buy a couple of these just in case you screwed up. These things, once you take the jet block off, are not that hard to push out. Sometimes they can be tricky. Get the gasket if you're going to try anything destructive, like adding heat. That being said, it's doable. It's doable to pop that out and drill it out. Also, of course, make sure the little main jet block deal, take that out and make sure that doesn't restrict you. I will show you the math later for how to determine the jet sizes and for how to calculate the needle sizes. The needle sizing is the trickiest part, in my opinion. It's doable. It's not impossible. I've never seen someone publish how to figure out how to calculate this stuff. So I'm going to teach you that. I didn't do anything wicked like slide cutting or anything like that. I matched the flow rate as best I could for what the stock carb does on gasoline, because this stock carb on gasoline works great. I didn't want to depart from what was working great. Now, some people go on about adding a power jet, and that's a lot easier to tune, and a power jet could probably cover up a bad needle problem. That may be an easier route to do a power jet or two rather than cutting a needle. However, these are not hard to make. So this guy is off a Keihin FCR39. Basically, all the early 2000s four-stroke carburetors had the Keihin FCR. You can get these needles all day. They start from a bigger taper, a bigger diameter. So it's like a 2.9 or a 2.8 something, and this is like a 2.4. So you can start from a bigger diameter to fit within your bigger hole that you drilled out better, more accurately. We'll get into that later, but I want to point out it wouldn't be very hard to make one of these without a lathe. What I would do, luckily I have a neighbor that I was able to work trade with some yard work, and he cut this thing down for me. If I did not have that, I would take a 3D printed guide, we'll call it. I would 3D print a guide that looks something like that. Just a piece of plastic that, oh boy, look at that, nice. That comes to a tapered point like that to match what I want. And you could put this in a drill chuck or a drill press, and you could hand sand that thing down and set it against your guide to check and see where you need to hand sand it down. This would not be hard to do. Anyone could do that. So as far as what I've shown now, you drill that by hand, you drill that in a press or by hand. One thing that I did to accommodate is I took diamond tip Dremel bit and I stuck that in there to deburr after the fact. You don't want a burr in there to eat up your piece of rubber on the end of the float, right? So we have hand drill with, isn't that funny? I would call this, right, a hand drill, but this is a hand drill. Anyway, so specialty tools, you need that. You need your metric engineer's drill bit set, and you need the hand drill and the other hand drill and sanding paper. And that should be all you need. You shouldn't need to have, 3D printer, of course, or wooden guide that can do what you want to do. And access to Google Sheets or Microsoft Excel or LibreOffice or any of the other free calculation suites. With that being said, that's going to cover it for the internal stuff. I saw these little Loctite, these little security screws came with Loctite, so I Loctited them going back in. The other very important thing to note is methanol is highly corrosive due to the oxygen in it, and it is hygroscopic, meaning it absorbs water vapor out of the air. So that means you need to drain the methanol out every single time you are done riding the bike. So I personally drain after every single time I ride it, unless it's a race day where I practice at 9 a.m., race at 11, race at 2, 3 o'clock. I don't think leaving it sit for half a day or so is going to be a problem. Very important to note, though, you must fill drain your whole gas tank, drain your carb bowl, fill everything back up with gasoline, and then run the bike on gasoline for enough time to burn off any methanol that is in the crankcase. When the methanol sits on aluminum, like the aluminum of your carb bowl or the aluminum of your case halves, it will pull the water in and it will react with the oxygen and it will literally eat through the aluminum of your cases. And if you leave it in with rubber gaskets, it will eat the gaskets. Now, I've been pretty militant about maintaining the fuel system, and I haven't had to change my gaskets yet. They are doing great. None of them have leaked, and none of them look in any kind of bad condition. As long as you're on top of it, you're going to be fine. I haven't done any destructive testing to leave a gasket sitting in methanol. I just don't need to. It's possible these stock gaskets will be okay. I think for some bikes you may be able to get rated gaskets. I don't know, but for me it's really not a long process. I just pop the fuel line off, drain the methanol back into the tank, take the 17 millimeter to the drain on the bottom of the float, dump that out, button it back up, put gasoline in it, start it up. I personally, since this thing is flowing 2.3-ish times the amount of gasoline, I personally have to leave the engine wide open, and it runs at about 4,000 RPM, barely, because it does not like having an air-fuel ratio of 4 or 5 to 1 on the full throttle end. So, interestingly enough, though, if you do run it on gasoline when the engine is cold, it will actually run pretty fine because the air density mixture ratios are much leaner, because when it's cold, it's a lot leaner of a mix. So, fun fact for you. But it was tricky to get going, so you have to kick it real hard and go straight to wide open and just leave it there, and it'll and it just takes forever to get going. You might even have to bump it to get it to stay alive. What did we cover? We covered fuel restriction from the gas tank, fuel restriction from the float, fuel restriction from the embossment around the float. We covered how to measure your fuel restriction rate changes, whether or not you're going in the right direction. We covered the basics of what to change out on jets. We will go into more depth in just a moment, looking at the calculation side of how to account for the right amount of fuel. We talked briefly about what is required on the upsizing and cutting of a needle to match with the upsized hole on your needle jet to accommodate more fuel. We talked high compression is not necessary but makes a huge difference. And we talked about how ignition advance needs to be fiddled with as well. So let's talk about ignition advance and my little horsepower dyno curves in a little bit more depth here. We got lucky there. That camera battery was about toast and it about ran out of storage. So we're on the crappier one now. Okay, so the reason I'm not showing the actual ignition curve numbers because my stator is in an adjusted position within the factory adjustments. The ignition offset amount for the programmable ignition unit might not be correct. So basically you have to tell the computer where the pickup is in relation to the rotating assembly. So since I have an adjusted stator plate and an maybe correctly measured ignition offset angle, so let's say if I'm looking at 30 degrees advance on my little programmable unit, that might actually be 34 degrees or 33. I don't know for sure. It's very tricky to measure the actual ignition offset without a degreed crank pulley wheel and a top dead center mark. I haven't gone through the trouble to calculate that out and print out a pulley or something, mark the case halves, and I just haven't gone through it. It doesn't matter so much what the actual offset angle is. What matters is the change between where the peaks are at within the RPM band. It's tricky to explain. So basically what I'm getting at is what I have as safe on my ignition advance might be dangerous on somebody else's engine combination because of the potentially incorrectly measured offset angle and the adjusted stator plate. I have no idea where mine is. It might be 10 degrees off. It might be 5 degrees off. I don't know. What matters is that you can track changes from modifying your ignition advance curve. So that brings me to number 2, my funky little laptop. That is a Raspberry Pi, which it has a program that I wrote from scratch to read the engine RPMs coming off the CDI unit. And if you can log engine RPM, you can do all kinds of cool stuff with it. So what I set it up to do is I set it up to calculate engine RPM for a quasi dyno pull. So what I have it set up to do is to log from 8200 RPMs up to the max, and it stores that data. So what I have done is, you saw it in the intro video, but it wasn't explained. But I have a push button rev limiter for the CDI that will hold the RPM at I think about 7400 RPM, something like that. So what I do is I go to the same section of pavement on the same weather conditions as best as is possible, and I will short shift the gears, 1, 2, 3, get into 4th gear, and I will hold the button down and I will go wide open throttle from a low RPM. The engine RPM will rise, it will hit the rev limiter, and it'll bounce off it. And once I reach the same position in pavement, I let go of the button. And when I let go of the button, that stops the rev limiter, and it's still full throttle, so it takes time, but the RPM will start climbing, and it does this straight to max, all the while recording engine RPM. Now, if you know engine RPM, and if you know the gear ratios and primary drive reductions and all that inside your engine, and you know the sprocket and chainring sizes, front and rear sprocket sizes, you can calculate, and tire size, you can calculate speed in miles per hour. Now, from speed in miles per hour, you can calculate acceleration as you're going along. From acceleration, if you know the mass of the bike and rider, you can calculate the force required to accomplish that acceleration. If you know the cross-sectional front area and coefficient of drag of you on your motorcycle, you can calculate the drag resistance, whether in newtons or in foot-pounds. If you know drag resistance and if you know the mass resistance, you can create a pretty darn good resistance curve, i.e. a torque curve. And from a torque curve, you can calculate a horsepower curve. So if you want to get really accurate, you also throw in tire rolling resistance. But I have absolutely no idea what the tire rolling resistance is for a knobby tire. So I just left that out. That is a linear relationship. So it only makes your horsepower curve have more horsepower. It shifts everything up. So, recap. Push button rev limiter. 4th gear. Same stretch of pavement. Same spot to start at on that same stretch of pavement. Roll on full throttle with the button down in 4th gear. Roll up to the line. Let go of the button. Let the engine go all the way to max. Get off the throttle, of course. Stop the data log record. Take the data and post-process it to calculate miles per hour, acceleration, and from those two you get drag resistance and you can get mass acceleration resistance. From there, you can calculate the torque curve across the entire RPM band. And then from that, you can calculate horsepower. So that's going a bit extreme. But when you have something like that, that is a program that can track changes, you can accomplish a lot. So the key is track changes, okay? My cross-sectional front area that I threw into the program is a total guess. I just Googled and found what some people said a certain motorcycle model, some sport motorcycle, was for a cross-sectional front area. I have no idea if it's correct. And I don't have the capability to measure literally the cross-sectional front area of me on the dirt bike. So, the same with the coefficient of drag. Also, just a total guess from Googling what people said motorcycles have. It doesn't matter as much having exact numbers if you treat your dyno as a change tracker rather than a record setter, right? So the numbers on the side column of my dyno chart aren't necessarily real numbers. It may say it's making only 24 horsepower. Maybe it is. Maybe it's making 29. Maybe it's making 20. Maybe it's making 31. I don't know. What's important is I can track that when the muffler was corked and it was running on gasoline, it was making, I think it was like 18 on its quasi horsepower count number, right? Which is probably drastically lower than it should be as an actual number, right? And now with methanol and ignition and high compression, it's sitting right about 24. So you're talking jumping from 18 to 24 by straight piping the muffler, getting rid of the stupid little turbine core thing. Where is that thing? I think it's silly looking. I forget it. Uncorked the thing. Methanol high compression ignition, uncorking. That's like a 25% horsepower gain. Huge gains. Huge gains. The important thing is the percent change. I don't really care if the actual number is accurate. What matters is that you can track changes. And I showed the little dyno curve at the start of the video, but it was kind of brief. But we'll throw it up again with that left column redacted. But you can see it's very good at tracking changes. So here's the main curve with the corked up exhaust, uncorked exhaust, both of those two on gasoline, and then we got the one purple curve in methanol. So methanol and high compression shifts your peak power to the left, which isn't a problem as long as you're still making more power, right? And so the uncorked gasoline runs were about 15% less horsepower-ish than the corked runs. Now, there's some funky data going on with the end of that curve where it kind of swoops up. I'm choosing to ignore that because that's probably not reasonable at all. The bike didn't feel like it was yanking acceleration like that. It's most likely due to the place where I typically do my dyno pulls. I run on a road real fast and I had to get on the brakes as soon as I could. So it's more likely that I yanked the clutch and the RPM spiked a little bit. So you're looking at an average there, right? So let me throw up the other curve. So this curve set is when I was making ignition changes. So you can see that there were some changes that went really far the wrong way and it did not help. And you can see also there's a 220 main jet in there. Did not help. possible that it would have helped if I played with the ignition curve more, but I haven't gotten to that stage. I'm thinking I'm going to try one jet size leaner rather than richer. That's kind of a long-winded explanation of what you need to do to validate whether or not your changes are having a good effect. I wouldn't rely on the good old butt dyno to do this kind of work. I would, if I were you, I would schedule dyno time with a local dirt bike speed shop, which means you're going to have to get a smooth tire. Or you could build a road dyno like I did. Unless if you're really tech savvy and can dedicate time to writing your own program, don't do it. There are aftermarket softwares that can do what you want. Whoa, Rick. Hey, bud. We talked about what to modify in the carb. We talked about how to verify whether changes are happening. We talked about what to change to increase your output. What we have not yet talked about is what changes to make on the calculation side to figure out size of your jets and needle dimensions and needle jet dimensions. We're going to go look at a computer screen. I'm debating on whether or not to just get a screen record software. Maybe we'll do that. All right, let's get to it.